In this video, we're going to look at section 2 of chapter 4, and the main idea of this section is that Newton's second law can be used to explain the motion of falling objects. A few essential questions that we're going to answer in this is: how are the weight and the mass of an object related? How do actual weight and apparent weight differ? And what effect does air have on falling objects? A few terms that we're going to use here, one that we might fall back on is viscosity, if you remember that from chemistry, weight, gravitational field, apparent weight, weightlessness, drag, and terminal velocity. So what is the weight of an object? Well, the weight is the gravitational force experienced by an object. And so it's the force that Earth pulls on the object. And because it is a force, we use the unit of newtons. And the gravitational force is a field force. And what that means is that it doesn't need contact in order to exert the force. You can exert the force from a distance. And that also means that it is directly proportional to the mass of the object experiencing it and the environment, essentially. What planet are we on? Are we on Earth? So that gives us this formula of the force of gravity is equal to the mass times baby g. And remember, what is baby g? That's the 9.8 meters per second squared, which you can write it as Newton per kilogram or meters per second squared. And so we call that baby g. That's our gravitational field. That's the acceleration due to gravity that we experience pretty much everywhere on Earth. So let's take a look at a situation here. Let's say Arnold needs to lift a 35 kilogram rock, and remember this is kilograms, so that's the mass. If he exerts an upward force of 502 newtons, what is the rock's acceleration? So we have a mass, we have a force, we're looking for acceleration. Well, this takes us to Newton's second law, and we can draw a free body diagram to just double check to make sure we have all the forces here. Well, we're exerting a force up of 502 newtons, and there's also the weight of the object, or the force of gravity, down. And we know we can calculate that by mg. And so if we have a force up and a force down, we want to subtract those two forces. So we can find the net force of 159 newtons. Once we get that net force of 159, now we can say that the net force is equal to mass times acceleration. Because remember, this is different than if we were pushing the rock in the horizontal direction. Because if we were just pushing the rock and ignoring friction, then that would be the only force. The force equals mass times acceleration. But remember, Newton's second law tells us that the net force equals mass times acceleration. So we have to subtract the weight from it, and then we can take that force, the 159, divided by the mass, and that gives us the acceleration of 4.5 meters per second squared. And so we can make sure that the sign makes sense, and it does because the net force is up. Up is positive, so the acceleration is positive. Let's talk about the weight and the difference between your weight and apparent weight. Now, weight is not an inherent quantity of an object. Mass is. Whatever your mass is, if you stand on the moon or you stand on Saturn or Jupiter, wherever, your mass is going to stay the same. However, your weight will change because the weight is the force of gravity acting on you. And so we can see a change in this weight, and when we see a change in this weight, we call that the apparent weight. And we see this, say, when you're riding in an elevator. So imagine riding in an elevator and standing on a scale. If you're just standing still, your scale is going to equal your weight. However, your apparent weight is that reading on the scale, and so if you're moving in the right way, that weight could go up or down. So basically what you feel, and you've experienced this in an elevator or on a roller coaster ride or something along those lines. And so that apparent weight depends on the direction in which you're accelerating and if you are accelerating at all. And a special type of condition in apparent weight is what we call weightlessness. And that's a condition where there's no contact force acting on the support of the object. So that's like if we cut this cable and all of a sudden the elevator starts to fall. Well, the elevator's falling, the person in the elevator is falling, so you feel weightless. the reading on the scale will be 0. The main thing you need to know here with apparent weight is that if we have no contact, so if there's no contact with the scale because we're in free fall, your apparent weight will be 0. If we are accelerating upward, your apparent weight will be higher than the weight on the scale. And if we are accelerating downward, then your apparent weight will be lower than what you would expect at rest. So let's look at an elevator problem here, and let's say you're standing in an elevator on a scale and you notice that the scale reads a weight that is less than your actual weight. So we want to know, is the elevator moving at a constant speed or is it accelerating? Well, because we have a difference from our actual weight, we know that this has to be accelerating. And so then we're then asked, if it is accelerating, what is the direction of the acceleration? Well, what I just said on the last slide, if we have less weight on the scale than what we would expect at rest, that means the elevator must be accelerating downward. So last thing we're going to talk about in this section is a drag force. And what is a drag force? Well, we live in a world that has friction and there's air all around us. And so air is a fluid, and anytime an object moves through a fluid, there is a drag. There's a force that is exerted by the fluid that opposes the motion through the fluid. So you can see this more clearly when think of jumping into a swimming pool and you swim by using the drag force. As you move your hands and feet through the water exerts a force on you to keep you afloat. Now, that same type of drag force happens in the air, it's just not quite as severe because of the viscosity of the air compared to that of water. And so the force is dependent upon a few things like the motion of the object and the properties of the object and the properties of the fluid, such as the viscosity and temperature, as I just mentioned, and how this object is moving through that fluid. So when you hear things that are aerodynamic, that means that they have a very low drag force exerted on them. A piece of paper falling has high drag force. It's not very aerodynamic. Drop a pencil, much more aerodynamic. And that has to deal with the surface area of the object. So when you drop something and there's a point where this drag force starts to even out and equal the force of gravity. Well, when that happens, we reach something that's called the terminal velocity. And that means it's the highest velocity that we're going to reach based on the drag force that's up and the force of gravity that's down. This stuff is just purely conceptual. We're not going to really do any math problems dealing with the drag force or anything, but I just wanted to talk about it a little bit so you get an understanding. So hopefully in this part of the video you were able to answer these 3 questions and got a little idea of this vocabulary. Now moving on into the final section of chapter 4, we're going to look at Newton's third law. So we've seen Newton's first law, where any object in motion is going to stay in that motion unless an outside force acts on it. Newton's second law tells us that a net force, if there is that outside net force on an object, well, that net force has to equal that object's mass times its acceleration. And then Newton's third law tells us that all forces occur in interaction pairs. One way you may have heard this before is for every action there's an equal but opposite reaction. Newton's third law is one of the easiestly quoted laws. However, it is one of the most misunderstood laws. In this, we're going to answer 2 essential questions. What is Newton's third law? And what is a normal force? And we've talked a little bit about this before already. So we're going to use some new vocabulary of interaction pair or Newtonian pair and Newton's third law, tension and normal force. So what is an interaction pair? Well, whenever there is a force, so say some object A is exerting a force on B, Newton found out that it is impossible to have just one singular force. If A exerts a force on B, B has to in turn exert a force back on A. And we call these 2 forces the interaction pairs. And so what this means, if I push on the wall automatically pushes back on me with the same force. that I'm pushing on the wall. And this idea is basically how we are able to walk down the hallway. As we push on the floor pushes back on us, and that propels us forward. And so the interaction pair of the two forces are always in opposite directions and have equal magnitudes. And so that's important. They're opposite directions, equal magnitudes, but the most important part of interaction pairs is that they operate on different objects. Okay, so whenever we have two forces that are Newtonian pairs or interaction pairs, they act on two different objects. A exerts a force on B, and then B in turn exerts a force back on A. So those two forces are on two different objects. And so the mathematical way to express Newton's laws is just saying the force of A on B is equal to the negative of the force of B on A. This just shows that they're opposite directions. So a way we see this soccer ball is sitting on the table, and that table just so happens to be on top of Earth. Obviously, this is not drawn to scale. But the soccer ball exerts a force on the table, but the table then exerts a force back on the ball. And the Earth is pulling on the soccer ball, and the soccer ball is in turn pulling on the Earth. However, the force that the soccer ball pulls on the Earth is so small compared to the force, or excuse me, compared to the mass of the Earth that we hardly notice it. And so the soccer ball has two forces acting on it. It has the force of the table up and the force of gravity down. So looking at the free body diagram here, we see that here are two forces, up and down. Now the reaction pairs to these two forces do exist, they just don't happen on the soccer ball. The reaction pair of this top force here is the fact that the ball exerts a force on the table. And the reaction force of the ball's gravity is that the ball is exerting a force on the Earth. So looking at a problem here, you're walking along when you slip on some ice and fall. For a moment, you are in free fall. During this time, what force do you exert on the Earth if your mass is 55 kilograms? Well, in order to find this, we can draw a situation. So here's you, you're on the Earth, and the force that the Earth pulls on you is going to be equal to the force that you pull on the Earth. And so let's figure out what we know about Newton's third law. Well, we know that if we find the force that the Earth is pulling on you, that can be the same magnitude as the force that you pull on the Earth. Well, the force that the Earth pulls on you is just the mass times baby g. So your mass of 55 kilograms times 9.8, then you can get 540. Well, we say that the magnitude is 540. If we want to know the direction, you're pulling the Earth up toward you. And like I mentioned earlier, 540 newtons is completely insignificant when you're dealing with such a large mass of the Earth. And so we can evaluate the answer to see that you would expect it to be equal in magnitude and opposite in direction of the force exerts on you. So last thing we're going to talk about here is tension. Now tension is exerted by a string or a rope. And so it's a way to translate a force. So if we have this bucket hanging on a rope and it's attached to the ceiling, well, the ceiling is not in contact with the bucket. However, this rope is in contact with the bucket, and the rope is in contact with the ceiling. And so we call this force that is exerting up from the rope onto the bucket, we call that the tension force. And one of the things that we need to keep in mind is that the tension in the bottom is going to equal the tension in the top. So that force that pulls up on the bucket is the same force that pulls down on the ceiling. One more thing real quick here. To bring back the normal force, we talked about this a little in class, but remember the normal force is perpendicular to the surface of contact, and it is exerted by that surface of contact. If you have just an object sitting at rest, the normal force is going to equal the weight. However, if you lift up, if you exert a little force on the object by lifting up, you decrease the normal force, whereas if you push down, you increase the normal force. So hopefully in this video you're able to answer these essential questions and you're able to define this new vocabulary.